continue straight from previous video where we discussed the reinforcement of the slabs. Now like to get the concept of calculating the design moments. Now some notes here before we move on straight on the calculation of design moment, because we need to understand what moment causing the slab to deflect more and which side we're going to take as a primary. So in a slab supported on four sides, so if you have a slab which is supported on the four sides, as you can see in our examples that a slab is supported on the four sides, I can show it to you here. That slab is supported on the four sides. We are designing on these beams. All the slab are supported by the four sides. Now in that case there are significant bending moment in two perpendicular directions. So let's say in x directions, in the y direction and in the x directions, and particularly when you have Ly over Lx equal to less than or equal to 2. So if you take the ratio Ly over Lx equal to 2, then you will have significant difference in two perpendicular direction. It means that if you calculate My and Mx, they have significant difference in the moment. An approximation of the behavior of the rectangular slab simply supported on four sides is as follows. Consider the two strips spanning in the short Lx. Please note, how do we decide whether it's Lx or Ly? It's not a horizontal axis and y axis in the slab. The Lx is classified as a short span. So if you compare two lengths on the both sides, the Lx goes to the shorter span and Ly goes to the longer span. For the same mid-span deflection of the two strips, so let's consider this strip that is along the y, and let's take another strip along the x. So if I just look at the pictures here, if I redraw this one here with the length Lx and the W load W, let's put this W load as a x, Wx. Okay, so this along this one is Wx. Wx is a share of the W carried in the short span. So this is total W. How much load will be carried in along this span is Wx. And Wy, let's say taking this line, Wy is the load sharing in the long span. So Wx over Wy. So if I let's work out here. 5 Wx Lx to the power 4, 384 here. It's basically the deflection on this one, let's say equal to deflection. But because at this particular point, if you are taking the mid span deflection at this particular point is the same. If you are taking this span or this span, the beam the slab will deflect at this particular point is the same. So this deflections due to Wx equal to Wy. So this deflection at the midpoint is exactly the same. In that case, if I want to calculate 5 Wx L to the power 4, 384 EI and 5 Wy, so I'm taking this, let's say delta y. So let's say this is delta x and this is delta y. And if we take the deflection equations, then if you cancel these both sides, 5 cancel, 384 EI cancels, you will end up with Wx over Wy is equal to Ly power 4 over Lx power 4. So that Wx is equal to Ly power 4 over Lx is equal to Wy. What is basically saying that the larger portion of the load is carried in the shorter span direction, and hence the moment in the shorter span are larger. So what is basically saying that which strip will carry more load? This shorter span will going to carry more loads. As you can see, Lx and Ly over Lx is greater than 1, okay, because this is the longer span over shorter span. So Wx is equal to some value times Wy. So Wx is larger value and the moment along the Mx is larger. So therefore, in our examples, we are going to have a primary direction, the load going on the primary direction, the reinforcement in the primary directions along the x would be our primary reinforcement. So design for reinforcement in the primary x directions are shorter span. So we need to design for shorter span. Now Lox and Ly we calculated previously. Basically this one talking about Ly is equal to this L, take away 2 times 0.7. So it's basically L, take away 0.7 A support L minus 0.7 A support on right. So what is they talking about? That okay, I think in the last video we discussed that if you have this length which is 7500, then A support is the half distance, which is 250 times 0.7 and 0.7, it's give me this 7150. and 5150 we discussed in the previous video. So if I take the ratio, that's give me 1.39. And please again note, Lx is shorter span, Ly is a longer span. Few more notations here. I rewrote these pictures because I did not draw, I don't draw this whole figure again and again. So now onwards I will do this part only, but this hex I'm representing as a continuous edge, and this hex is continuous edge, but here they are discontinuous. That is the word they use in the standard. AS3600 use this continuous edge and discontinuous edge. More structural engineering, they call it interior beams. So all these are interior beams. So if I talk about this, these are interior beam, interior beam, interior beam, interior beam, interior beam, and these are interior beams, and these are the they call spandrel beams. So at this corner they are spandrel beam, or you can say edge beams. Okay, so that is just a vocabulary. Now calculations. Now the calculations of, let's say, larger portion of the load is we discussed this one. Now I redraw these pictures here. The pictures meaning that I redraw this corner here. Now these corners that I show it to you here, that has a bending moment, let's say the W. If I take the strip here along this one and it has a W load, let's say this W load, and if I redraw this one, this is a continuous. Okay, these are continuous one, but let's say consider this one only. So in that case I can draw the bending moment diagram. At the supports you have a negative moment, at the mid span you have positive moment, at continuous supports you have these negative moments. Now we can use the structure analysis and solve for this one, but the standards provide the simple calculation. So if you like to calculate this positive moment at the mid span, let's say along the AAX direction, we can use clause 6.10.3.2. That is given here, positive design bending moment at mid span. Please note, we are working with mx, we are not working with this my. Okay, you can draw the bending moment diagram and my, but I give you this notation that my is not required because mx is the larger value. So mx equal to beta x, because if you want to calculate my, there is a equation here as well, but we are working with the mx, which is the moment along the x. So positive mx star is equal to beta x fd lx square. Now how do we find beta x? Just over the page there is a table given to you. There is a tables given to you. Table 6.10.3.2 is a bending moment coefficient for rectangular slab supported on the four side. Ductility class N reinforcement. We assume N12 bar, so class N ductility. Over the page, I think there is a one more here. That is the bending moment coefficient rectangular supported on the four side. Ductility class N and ductility class L reinforcement. Okay, so if you have a class L reinforcement, we can use this one. But here we are going to use this 6.10.3.2a. Now in this case we are using these conditions to adjacent edge discontinuous. I can again show it to you here in this examples. We have two edge discontinuous, that is two edge discontinuous. Condition 6 and Ly over Lx, I think we calculated Ly over Lx 1.39 is almost 1.4. So you have 1.4, condition 6, you have beta x 0.055. So if you substitute 0.055 beta x 9.6, I'm just using these equations here. FD 9.6, I think we calculated that FD, which is your design load, factor design load, 9.6 kilopascals. 9.6 kilopascals times the length 5.15 square, that is Lx square, that is shown here, give me 14 kilonewton meters. Now we also need to calculate design bending moment at interior spans over here, minus mx to minus mx at continuous support. So we are talking about what is the design bending moment at this particular beams. So that standards again give you here in the B part. It says that you need to take it 1 times 1.33 at mid span value. So we found that mid span value was 14 kilonewton meters. So you can just multiply by 1.33, it gives me 18.6 kilonewton meters. And we also need to find the design moment at this discontinuous edge. So it says here continuous edge, okay, so in B it says that continuous edge, so this is continuous edge, or we can say that interior beam. Over the page, let's talk about the C, which is a negative design moment at discontinuous edge. So this is discontinuous edge, and that is design bending moment is just 0.5 times the mid span value. Okay, so 0.5 times 14 is give me say 1 kilonewton meters. So that is the bending moments that we calculated. These bending moments allow us to see what reinforcement require at the mid span, what reinforcement require at the interior span or interior supports, and what reinforcement required at this one. Please note here we need the bottom reinforcement, here bottom tensile reinforcement, here top tensile reinforcement. We continue in the next video calculating the reinforcement. Thank you.